Hello, everyone. So thank you for this opportunity to present our recent publication on evaluating the performance of an estimation method called pi for bias reduction in association studies. So real-world AHR data often suffer from phenotyping error due to imperfect phenotyping algorithms. The true disease status Y is often not observed, and what we have is only an EHR-derived phenotype S, and this S is often not equal to Y. So if we directly use S and the exposure X to fit a model, then we would have a biased estimator of the true association beta 1. So the true relationship between S and the exposure X can be expressed as a function of the true association beta 1 and the sensitivity and the specificity of the phenotyping algorithm. So suppose we know the phenotyping algorithm well and we know the true sensitivity and the specificity, then we can plug them in the formula and then we can achieve an unbiased estimator of the true association using the maximum likelihood estimation. However, in practice, it can be hard to determine the true correct specificity and sensitivity. And if they are misspecified, then again, we have a biased estimator. To overcome this challenge, pi method was proposed by Huang et al. In 2018. So this method only requires specifying a prior distribution of the sensitivity and specificity instead of the exact value of the sensitivity and specificity. And then the pi average over this possible range of values by adopting the integrated likelihood. The pi estimator can then be achieved by maximizing this integrated likelihood. So in our paper, we aim to evaluate the performance of pi under a wide spectrum of real-world scenarios. And in addition to bias reduction, we want to study how pi improves type 1 error and statistical power, and also how does the choice of the prior distribution impact the performance of pi. To answer these questions, we conduct simulation studies under different settings where we try to mimic the real-world setting. And in addition, we evaluate pi on synthetic positive controls on COVID-19 infection constructed based on known negative controls. In our simulation study, we evaluate the bias, type 1 error, and the power of pi. And then we compare pi with the naive method where a logistic regression was fit using the outcome from the phenotyping algorithm and exposure X, and then the maximum likelihood. We also compare it with the maximum likelihood estimator with known sensitivity and specificity. We fixed the prevalence of the exposure at 30%, and the prevalence of the outcome Y under unexposed varies from 5% to 50%. We fixed the effect size at log 3 in bias evaluation and 0 in type 1 error evaluation, and we let it vary in power evaluation. So the true specificity we set at 99%, and the true sensitivity is 65%. We used a uniform distribution for the prior distribution of specificity, and we fixed it at uniform 95% and 99.99%. So for the prior distribution of sensitivities, we let it vary under different means and spreads because we want to evaluate how does it impact our pi estimator. We also tried beta distribution and logic normal distribution as prior distribution in addition to the uniform distribution, but we only present uniform distribution here because they convey similar message. So this box plot presents the estimation from 200 simulated data, and then each box represents a different prior distribution on the sensitivity. So the x-axis represents the prevalence of the outcome, ranging from 5% to 50%. The blue box represents the pi estimator, and then the yellow box represents the naive estimator. So we can see that pi was always closer to the truth compared with the naive estimator, and this indicates a bias reduction. And with regards to the prior distribution of sensitivity, so as it becomes more variable, meaning that it has larger spread, for example, from on the top from left to right, the spread of the distribution increases, and we see that pi shifted away from the truth. And the influence, and then we can also see that the influence of the prior distribution was larger when the prevalence of the outcome become larger. For type 1 error and power, we find that they have similar performance across all the methods. The type 1 error are always around 5%. The power increased as the effect size increased, and the power is smaller than the gold standard power, where the outcome, the true outcome, was known. I'm going to hand over to Iris for real-world inspired evaluation.
Thank you, Naimin. Can you hear me?
Yeah.
Okay, great. So to further investigate the robustness of pi under real-world conditions, we conducted evaluation using data synthesized the distribution from our existing COVID-19 infection study. The outcome we used is the binary indicator of COVID-19, mimicking the prevalence of in our previous study in the effectiveness of vaccination. And to test how well the algorithm works, we created a synthetic positive controls from the non-negative controls as the predictor to make sure that we have the true estimation of effect size. The prevalence, the sensitivity, and specificity in this setting are also informed by the previous study using real-world electronic health record data such as PISNet and CHOP studies. Next page, please. Yeah. So the sample size we used for this evaluation also follows the existing study using patients from September 2020 to April 2022. Here we constructed the synthesized positive control as predictors using negative controls, including the disorder of optic nerve and visual pathways, the visual disturbance, the disorder of choroid and retina, and disorder of sclera and cornea. Now, the constructed synthetic positive control preserves the characteristic of real-world data while have no effect size to allow us to evaluate the result of pi. And we considered multiple effect size to ensure that pi remain valid across different scenarios. As the true sensitivity and specificity were assumed to be unknown when we using pi, we set the prior distribution of sensitivity as a uniform from 0.79 to 0.95, and also a specificity. Yeah. The purpose of this evaluation is to mimic the real-world evaluation and to see how if the pi still works. And the next page, please. Yeah, we found that pi consistently outperformed the naive estimator, especially when the effect size are higher, and the naive approach underestimates the effect size, and it becomes worse as the effect size increase. And pi maintains a relatively accurate estimation across different strengths of relationships. So we interpret that the cumulative results reflect that would likely occur in the real-world electronic health record studies, and is most beneficial for estimation. So for time method, could you pass to the final slides? Yeah, so this paper basically answers 3 questions, like how well does pi perform under a wide spectrum of operating characteristic under the real-world scenario. And we found that it effectively mitigates the estimation bias due to phenotyping error. And we also want to see if pi improve the result in the type 1 error and the statistical power relative to the naive result. And we found that its main benefit lies in the bias reduction rather than the hypothesis testing improvement. And finally, we want to see how does the choice of the prior distribution impact the performance of pi. And we found that the impact of the prior is very small for low prevalence outcomes.